It's okay.
I'm not going to speak too much about masses.
Sorry? Within this area.
No, tampoco. Lo ideal sería que
you come too much.
¿Sí? ¿O si es útil?
Si no, hay que mandarle un mensaje, ¿no?
Okay, so let's start. Welcome everybody. Also greetings to the friends and colleagues from Glasgow that are probably looking after our webpage today. Hi. But today we have Pavel Paulau. All of you probably know him. He has been with us already for close to a year already. Yeah. And he will talk us today about work on localized vortices. He has been doing here in VCSEL purposes like in people. So, please.
Thank you. First of all, I should say buenos días a todos.
Buenas tardes.
Buenas tardes. Second, I should say thank you to Maxi for giving me opportunity to work with this institute. Third, I should ask about people with whom this work was done. So it is Daniel Gamila, Paulau from here, from IFISC, Torsten Ekiman and Willy First from University of Stasvai, Natalia Loiko from Minsk, and Nikolai Razanov from St. Petersburg. We are in Mallorca. Today is 9th of December. Temperature outside.
Today is January.
Oh, sorry. But the sense is that winter. Now. And the temperature outside is plus 15, 18. Okay. So my talk will consist from 3 parts: introduction, vortices and lasers, and conclusion. First of all, I would like to speak about most known spiral solutions in nature. These are whirlpools in water. So here you can see a picture of a very big whirlpool in ocean. Apparently, such big whirlpools can be formed by big oceanic streams, which go like this. Okay, such whirlpools can be formed also behind ships, near bridges. They can be reproduced in bathroom, and also at motion through pipes. And since water was used by people long time ago, the first quantitative descriptions of spiral solutions are related to water whirlpools. And one of those works which I would like to mention is the work of Helmholtz from 1858. The next important work which I would like to mention is published by Lamb. This is a book called Hydrodynamics. The first edition was done in 1945, and then this book passed through many editions, and now it's a textbook about hydrodynamics. Okay, now I would like to speak about one important property of world which is around us. Most of systems around are dissipative. That means if you have some state and this state has some energy, this state will lose energy with time due to dissipation. In this particular example, you see the water whirlpool, which is supported by some energy. And this energy comes from tube which sucks water downstairs. So this is a small bridge, and this particular whirlpool will survive long time until we have this stream of water. But the whirlpools behind ships are less lucky. They will die because they don't have permanent support of energy. So the support of energy is important for whirlpools. Okay, with the run of time, many new areas became available for people in previous century. For example, people were able to create Bose-Einstein condensates, which are states with very low temperatures. And of course, observation of vortices became possible in these systems. Here I give reference where they give vortex-like states in Bose-Einstein condensates. Next, people got light amplification through simulated emission. So they created lasers. And of course, the idea to create vortices in laser field came to somebody's head. So to my knowledge, this idea came to several people independently in 80s of last century. So here I show last experimental results related to observation of vortices in semiconductor lasers, in VCSELs. Not surprisingly, this object is very interesting. This is spiral solutions, and many researchers are interested to study this phenomenon. And therefore, there is permanent growth of interest to this topic. For example, this diagram represents the number of publications devoted to this topic in physical review database. For example, in 60s it was only 56 works, in 80s it was 250, and during last 10 years it was 1,500 works devoted to vortices in physical review database.
What happens if you normalize to the total number of papers in physical review?
I haven't done it, but I'm saying that the topic is growing.
5 years ago.
I'm not sure what happens if you
I'm not sure too. So this is good. I was asked this question, but I have no time to make this comparison. But the interest is growing. Maybe not related interest, but interest. Okay, now I would like to give here one nice example of spiral solution. This is spiral galaxy. Here I give another example of spiral solution, which is Belousov-Zhabotinsky reaction. There are also spiral solutions in biology, for example, in the patterns of activity of heart or brain. Here I give next example of spiral solution, which is tornado. Tornado, for example, can be frequently observed in America. Really? Okay, I didn't know. Maybe not so big. Okay, so here you can see another example of spiral solution, which is smoker vortex ring. So people who smoke can do, and they have ring. And this ring is reproduced in a laboratory of University of Warwick. So this is laboratory experiment. They use gas, they use paint, and they show what it is. Okay, in this slide I would like to speak about dimension, geometry, and topology of vortices. If I would ask you, is it possible to have vortex in 1D? So probably most of you, or some of you, or I don't know, will say no, in 1D it's impossible. My view of this problem is the following. If you have singularity in some point in one dimension, this is analogy of vortex. For example, here I show analytic solution of some important physical equations, which is a module of Duncan hyperbolic. And this function has singularity, and it is very similar to one-dimensional vortex. But these are speculations. Forgot about this. Let's go to dimension 2. If we have two-dimensional space, clearly that in this space you can have vortices. And basically they are reproduced by vector field like shown here or here. By the way, this vector field is the full analogy of phase space and the point of type center from linear dynamical systems theory. And this is of type spiral. Now I would like to go back to this slide, to tornado. Just to consider it as example. If you want to characterize this solution, how can you do it? For example, you can just take horizontal plane and you can define in this horizontal plane vector field. What does it mean? For example, in each point of this plane you should define the velocity of wind, direction and velocity. Okay, now imagine that you move this plane slightly above in vertical dimension. You will see basically almost identical picture of structure of vector field. You move above, and you will see basically the same. Of course, it's slightly different because you cannot create infinite conditions, equal conditions. Here you have ground, above you have space, and you cannot reproduce infinite homogeneous structure of this system. Okay, now I would like to discuss the following point. What should be velocity of wind in the center of tornado? So this is correction of, so I took this horizontal field, this vector field, and plotted here. Imagine that we have some non-zero velocity in the center. What does it mean? If we are infinitesimally close to this point but slightly above, then we will see that the wind blows to the right and with fixed velocity. If we are infinitesimally close to this point but below, then the wind blows to the left. This gives controversy because effectively in the same point, wind blows in two opposite directions. This controversy can be removed if we suppose that velocity is zero. So apparently the velocity in the center of tornado should be zero. The next point which I want to emphasize is what should be the velocity of tornado far away from the center. apparently you can sit in the car, drink beer, and observe this phenomenon. So that means that velocity near your car is very small, and you are rather safe. Rather safe. That means that here, far away from observer, you have effectively zero velocity. What does it mean? That the structure of distribution of amplitude of velocity is kind of ring. You should have some maximum. So this is minimum 0, this is minimum 0. Here you should have some maximum. So that means that this should be some ring. Okay, apparently for conservative systems it should be like this of type center. For dissipative systems it should be like this of type spiral. Now I would like to speak about another examples of vortex solutions. Up to now we spoke about tornado, but let's speak about optical field, which is characterized by complex variable. That means that in this plane we should give complex field, or in other words, in each point of this plane we should define complex variable. So complex variable has amplitude and phase. And vortex for this complex variable will be just ring of rather high amplitude and variation of phase. So if you change azimuthal angle like this, you should observe change of amplitude of complex field equal 2 pi or 4 pi or 6 pi. So you have change of azimuthal angle 2 pi, but change of amplitude of complex field, as I say, 2 pi, 4 pi, and so on. And this is characterized by topological charge. So this is quantity, this integer quantity, which make connection between period of azimuthal angle and period of complex field is called topological charge, and it can be any integer number. And this is called topological charge because related to the word topology, because you cannot transform one vortex with one topological charge into vortex with another topological charge just by smooth variation. Okay, next let's go to dimension 3. I would like to speak now about strategies to be vortex in 3D. I have made above some examples of vortices, and let's speak about tornado. What is it? This is isosort model of isosurface of tornado. Isosurface is the surface which represents the position of points with equal amplitude, for example, of wind for tornado. So this how looks like tornado, here isosurface of tornado. Imagine that this is maximum of velocity. Okay, and velocity of course directed in each point, so you can take horizontal section. In each point it is tangential and like this, like this, like this. Okay, this is one strategy to be vortex in 3D. You have vortex in 2D section, and this vortex is homogeneously extended in third dimension. This is one strategy to be vortex in 3D. Second strategy to be vortex in 3D is following. We take this tornado, we do this, and we have smoker vortex ring, which propagates, rotates like this, or direction like this. And this is second strategy to be vortex in 3D. Another strategy to be vortex in 3D is represented by spiral galaxy. If you take spiral galaxy, you will see that it is spiral solution in plane. But in orthogonal direction, it is localized. It's not extended like vortex. That means that isosurface is degenerated into light. So it's localized in this direction, but vortex in this plane. Okay, next I would like to ask question. Is it possible to have to have ideal 3D vortex. Another strategy to be vortex in 3D. For example, what does it mean? It means that the isosurface of vortex should be like this. It should be perfect sphere. And I'm saying that for geometrical reasons, it's impossible to be vortex like this in 3D. Why? Imagine that you have this isosurface, and in each point of this isosurface is given, okay, suppose very complex number, which has amplitude and phase. To be vortex, you should take, for example, any arbitrary point of this isosurface and put the line around. And during this way, you should give 2 pi variation of phase of complex field, for example. If you will do the same, and you should do the same in second section like this, in third like this, and in all planes. If you will do it, okay, you define vortex in each plane. But immediately, if you will take orthogonal section like this, you will find that the phase in this orthogonal section is already defined and it is unchanged. So it is already not vortex. So this strategy is not valid in 3D. So vortex is effectively two-dimensional structure, and as I know, maybe you know, you can say, add to my presentation, another strategy is to be vortices in 3D. Okay, now let's go to optics. As I know, up to now, there are many implementations of vortices in optical systems. To my knowledge, there are implementations of this strategy in optical systems and the strategy of spiral galaxy. That means vortex in plane and localized in third dimension. So this is done in optics, but I'm not sure. Maybe such works exist, but I don't know whether it is implemented. Smoker vortex, ring vortex. Okay, why it is interesting in optics? There are 2 reasons. First one, because optical vortices have orbital angular momentum, and they are able to rotate micro objects. So that means if you have micro objects, you radiate it by light. This micro object absorb light and absorb all the angular momentum and start to rotate. This is why it's interesting in optics. Second reason in optics why it's interesting in optics is because angular orbital momentum should have much more rich quantum properties than spin momentum. This is the second reason why it's interesting in optics. Now I would like to say a couple of words about work of Emilio, about dynamical regimes in 2 couplet Ginzburg-Landau equations. So in this system, you can observe the regime which is presented here. Here, the instantaneous distribution of phase is shown, and here, instantaneous distribution of amplitude of complex field is shown. And you can see some spots here. They are black. They are singular points representing the vortex. But what is different here is that amplitude of field is not 0, far away from core of the vortex. That is main difference in relation to the vortex states about which I spoke before. This is so-called vortex glass. Moreover, I would like to make short comparison of this vortex glass regime to what I showed in in this slide. So namely, one dimension tangent hyperbolic solution. So this is direct analogy of vortex where you have constant amplitude far away from center. But main interest of this talk is self-localized vortices. That means nothing far away from center, 0. Okay, now I would like to say what we did. Actually, we have considered. Yes. So this I told that my talk is 3 parts: introduction. Now we go to vortices and lasers. Okay, so last week you have excellent opportunity to find out why vertical cavity surface emitting lasers are very interesting, because they are used in telecommunication systems. So this is extremely well studied topics, and people study different arrangements based on VCSELs. Okay, we did the study of the system based on VCSEL, which is shown here. You have VCSEL here. Its emission is collected by the system of lenses in some region here, focused like this. Then in this region you have diffraction grating, which provides reflection of the light back into the cavity, and also, since this is diffraction grating, it provides frequency selection of light returned back. Okay, we insert also polarizer into the feedback loop to kill one of linearly polarized components, to consider only linearly polarized emission. And we put it, okay, we can put also here the special filter, which can provide filtering of Fourier modes which go back into the VCSEL cavity. Such a way we can control the polarization, transfer structure, and the frequency of the emission returned back into the VCSEL cavity. So we can control many things of this compound system. Below I will speak about results related to this system, but without special filter. So special filter is helpful tool, but it's not necessary for many results which will be explained below. Okay. 5 years ago, my supervisors thought that we will study VCSELs. My supervisor gave me the article of Martin Regalado and Maxi and told that this is proper way to make modeling of VCSELs.
Good supervisor.
Yes. And yes. Okay. I took this model, I look at it, I see 2 equations for linearly polarized component, one equation for carrier dynamics, one equation for magnetic sublevel populations, and my supervisor say we should include special effects here, we should also include frequency selective feedback. I look at it and I see, okay, so this is good, but I would prefer something more that's too complex for me. And I inserted polarizer into this scheme to kill part of this model, big part of this model. We remove immediately the equations for magnetic sublevel populations, and we remove immediately equation for second linearly polarized component of the field. Such a way, we have only 2 equations from Max's model, which is equation for one component of the field and equation for carrier density. But then it was not enough for me. We have still 2 equations, and I say to my supervisor that since we are interested in modeling we are interested to find steady state solutions, we can remove equation for carrier density, because steady state solutions are equal. So adiabatic elimination of equation does not remove existence of steady state solution. Of course, carrier density dynamics can influence on the instability, but as we find out later, that usually it helps to stabilize steady state solution. Okay, so after making these simplifications, we have formulated this model. So now I will explain what you will ask, what is here from VCSEL? I will say the only one term here, which is line width enhancement factor. But still, it this model describes better results of experiment. So let's look what is in this model. We have equation for intracavity field, this one, and this equation contains first losses, so dissipation, light goes out of cavity. It contains saturable gain. We provide pump to the laser and gain, and it is saturable like this. It has also this term, which is effect of Leibniz enhancement factor, and in this formulation it is self-focusing or defocusing depending on sign of alpha. Next, we put here diffraction in cavity. So now I will not speak about this, I speak about last two terms. Last two terms are responsible for the choice of reference frequency and for the detuning of the VCSEL from the central line of frequency selective elements of the grating. And frequency selective feedback is described by addition of this term. So it can be done in integral differential form, in integral form, but it can be also transformed into differential form, which is shown here. This is described in literature. So differential form is, to me, it's rather simple. It's just one more differential equation. Okay, so we have this system and we study it. First, what is interesting to us is to study stability properties of zero solution. Zero solution is a solution for which field Ex and Fx are zero. Evidently that if you put 0 here, derivative is 0, 0 here, everywhere is 0. So 0 equals 0, trivial solution. And this solution is very important. Why? If it is stable, then we don't have emission. Field is 0. But if it is unstable, field starts to grow, and we can see the generation of this system. In this slide I show the stability properties of trivial solution. In horizontal axis I show transverse square of transverse wave vector. In vertical axis I show pump current. And we have two compound effects in this system. First effect is frequency selection. Second effect is diffraction, which provides detuning of off-axis modes from on-axis modes. That's joint effect of frequency selective feedback and diffraction provides reduction of threshold for some off-axis modes, as shown here. So you have reduction of threshold. Trivial solution became unstable here in this region of K perpendicular and pump current, and you can see emission. Changing these four subplots correspond to different values of detuning between laser and grating. So such a way you can changing this parameter, you can shift this instability region to the left or to the right. Okay, at some parameters you can reach this situation when you have zero solution stable here, unstable here, stable here. In previous works,
So what is the blue line, the dashed blue line? With the
this one, this is frequency selective
that's
line.
Okay.
Sorry, I'm not understanding this graph. So this k-square perpendicular, how that relate that to the previous equations?
Here, if you will put this operator in Fourier transverse space, it will correspond just to multiplication of, this is transverse Laplacian, describing diffraction. In Fourier space, you can replace this by k square minus k square. And actually, these are stability of zero solution with change of this k square. And this is k square, this is pump current, and this line represents the instability curve, modulation instability boundary region of zero solution. Okay, so we are in this situation. Here, the zero solution is unstable and system. I'm not sure that we have voice. For it's red.
Yes, that's okay.
That's okay. Okay. So other people shown that here in this region, without special degrees of freedom, you can observe bistability of zero solution and non-zero solution without special degrees of freedom. Okay, in our case, we've shown that when we add special degrees of freedom, we can see the excitation of self-localized states here in this region when we go from here to here, just changing pump current. And it is shown in the next slide very quickly, probably. So this is a very complex regime initially. It is extended. Sorry for this, but probably you can do it.
Is that experiment or is it
No, this is simulation, but experiment gives nearly the same result. Simulation. So initially it was a complex special temporal regime. We changed pump current and we can see formation of these bright spots. Experiment, of course, gives very different results in other contexts. Qualitatively the same, because you change pump current, you see some complex regime and you see spontaneous formation of these spots. Okay, now I would like to discuss bifurcation diagram of these states, which we had seen on previous slide. So if we will plot total power, which is integral over space of intensity, depending on pump current for only one spot-like self-localized state, we will see this picture here. The self-localized state is born here in bifurcation point. Then with increasing pump current, the total power grows, like shown here. Then after some point it starts to decrease. At the same time, here in this point, you have bifurcation point of second self-localized spot-like state. And increasing pump current, it grows up to this point where upper and lower self-localized states collide and annihilate, and this is saddle node bifurcation point of self-localized states. Now, I would like to say about stability of this state. Here, in this region, background is unstable. Therefore, you cannot have stable self-localized state because background is unstable. Here in this region, the self-localized state is unstable to drifting instability. What does it mean? If you put initially self-localized state motionless, it will start to move. So it was just spot and then it is moving spot. Okay, now in this region here, motionless spot is stable and we can observe it in simulation. Okay, so everything is confirmed by stability analysis and simulations. This part of branch represents the separatrix solution. That means if you are slightly above this solution, it provides switch to upper state. If you are slightly below, it provides switch off to trivial background solution. Now I would like to speak about excitation of vortices in this system. In this subplot here, I show the dynamics of real part of the complex field describing light, of the complex field Ex. Here I show the dynamics of amplitude of this field. And since this is steady state, the dynamics of amplitude is stationary. Actually, there is no dynamics. It's constant.
What is that?
This picture shows the dynamics of real part of the field.
In which system?
In above, just this, which we discussed above.
In the same equations.
In this
So
equation.
this is simulation of the same equation.
Yes, this is simulation of these equations which I explained. These are solution of this equation. So this is real part, this is amplitude, and amplitude is constant this time. Okay, so for lower two subplots you have the same real part dynamics, amplitude dynamics for another type of excitation. So how these vortex-like states were excited? Just putting initial conditions in the shape similar like this, like shown here, we see the transition to steady-state vortex-like solution, and the attraction basin of such a vortex solution is very broad. So you can modify such initial conditions in very broad range. Okay, you should be close enough, but you can do it in very broad range of functions. Okay, now these upper situations correspond to the excitation of M of vortex with topological charge equal 1. That means that around one period of azimuthal angle, you have variation of phase of complex field equal 1. So it is seen here that it's only one bright spot in real part. For this situation, this is vortex with topological charge M equal 2. And at variation at one period of azimuthal angle, you have two periods of modulation of phase of complex field, and you can see here in real parts you have two maxima, two bright spots. Okay, now let's go back to this bifurcation structure. Here I show the results for bifurcation curve of M equal 1 vortex, which we just seen, and for M equal 2 vortex. And basically the stability properties of M equal 1 vortex are the same like stability properties of M equal 0, spot-like localized state. So you have here unstable background, you have here drifting instability, which just results in appearance of motion. You have ring, vortex, it's unstable and it starts to move. Okay, here you have stable vortex with M equal 1, and here you have separatrix of vortex separatrix. And here you have similar saddle node bifurcation of vortex solutions. Next, I show here M equal 2 branch, which is much more complex in the sense of stability. So it looks very similar to these things, but stability properties are very different. Okay, here you have unstable background, here you have separatrix, it's very similar. Here you have stable region of M equal 2 vortex, but here you have three bifurcation points which give birth to three different modes. I show here the results of stability analysis of self-localized states. In this axis I show the real part of eigenvalues of stability problem, and here I show the pump current. And these are the same point, G1, G2, G3. And you can see here these curves which correspond to maximally unstable eigenmodes. The structure of each eigenmode is given in subplots. For example, this eigenmode corresponds to this line. This eigenmode corresponds to this line. This eigenmode corresponds to this line. Okay, now I would like to show how M equal 2 vortex evolve at presence of these unstable modes. So imagine that we are here in this region where vortex is unstable, and the evolution of this state is shown in this slide. So we initialize the system by vortex, this is perfect vortex, stationary but unstable. And you can see how it evolves with time. It starts to deform and there is transition to some more complex regime which looks like this. You have some compound system which rotates, but still it is here in the same position. Now if we decrease pump current to see the excitation of second mode, we will see the following. We have this vortex, it starts to move, you see, then it starts to, the first mode comes into play, and you see finally the complex regime which is shown here. It is more complex than in previous slides, so there are two modes which contribute into this regime. If we decrease pump current more, we see more complex destabilization which is shown here. So here instability is very strong, and you see decoupling of m equal 2 vortex in two self-moving states, like shown here. This work is unfinished, but I show here only the importance that here intensity is almost zero. Around, intensity is almost zero. So there is the idea that important is only this stripe, and in principle in the center, which is not very important singular point, vortex itself, we can put another solution, for example spotlight structure here, or another vortex. But current examples show that these states are unstable and it needs more work. Okay. So, third section of the talk. Conclusions. It doesn't look like it's not conclusions, but third section. So, we have this model which describes our system. What we do? We do one nice thing. We do one more simplification. We make expansion of saturable thing into Taylor's area, and we keep only two terms. Next we do one magic thing. We replace variable ax by psi, fx by f, introduce some additional variables, and we have after that this system, which is this system. And up to now I can say that spotlight solutions are solutions of the systems of this system. I haven't checked still vortices, but I guess they should be also solutions of this system. And this equation here is Ginzburg-Landau equation, which is nonlinear, dissipated generalization of nonlinear Schrödinger equation. So it can be useful also not only in optics but in some other fields of physics. Okay, except of this Schrödinger or Ginzburg-Landau equation, we have here linear coupling to linear equation. It is known that in one-dimensional case, this Ginzburg-Landau equation has analytical solution in the form of second hyperbolic. But this solution is unstable in Ginzburg-Landau. Addition of such a linear equation can stabilize second hyperbolic solution. I found it nice to study some scaling laws. For example, Manuel asked at some point, what is the scaling law of at approaching of bifurcation points? And this question can be addressed in this case analytically.
So, what is the gain in this equation?
Sorry?
What is the gain?
Gain?
Yes, I say.
G2.
But it's negative. So it's not a gain. There is some.
The sign here. Minus, minus, plus. No?
I don't see it. I see everything is the gain.
Gain?
I mean, the J2 has negative real values.
Yeah, G0 can be positive with this.
The G0 is the real values minus kappa. So I don't see where is the gain.
Plus, here is minus, you see? Here is minus.
That is one. So there is no linear gain, so you have only non-linear gain.
Non-linear gain. Linear gain too, but there are both non-linear and linear gains. But these are free parameters. You can choose whatever. In proper choice of parameters, they will represent the situation which was considered.
I will not call this a laser. I see something like something bistable.
It represents the dynamics of laser almost identically. We can see represents the same bifurcation diagrams, the same things. So okay, some people call this model of laser. Okay, but it can be related to other things. It's Ginzburg-Landau equation. At least I know the works of Boris Mohamed about couplet waveguides, and it is described exactly by this system. Okay, now to controversial part of the talk. This is still conclusions. These are still conclusions. Quantum people will beat me by something heavy, but I would like to make some analogies. Okay, so let's imagine that we have particle, free particle. It should be and nothing else. It should be described by Schrödinger equation. Solution of Schrödinger equation for free particle is sinus, and that means that the probability to observe particle is equal for every point of space. This is already not property of particle, because intuitively I would say that particles should be localized. Okay, now if we add potential, like particle in potential well, then the wave functions of Schrödinger equation with in the potential well, particle in potential well, the wave functions of particles became localized. Okay, but they are localized externally by adding of external potential. I'm saying here that in nonlinear Schrödinger equation, which has one additional cubic nonlinearity, there is second hyperbolic localized solution, but it's unstable. And I will say that this second hyperbolic solution is direct analogy of wave function. Okay, so Schrödinger equation, nonlinear Schrödinger equation, some analogy. So I would say that particle in free space without any potentials is better described by nonlinear Schrödinger equation, which has localized solutions, though unstable. Okay. So now I would like to say a couple of words about odd or even vortices.
I didn't understand. Was the statement that the free particle in quantum mechanics is better described by the nonlinear Schrödinger equation than by
Schrödinger equation?
Are you aware that
The particle, in my opinion, is better described by nonlinear Schrödinger equation than by Schrödinger equation.
a quantum free particle?
Sorry, I'm not competent. Particle. Schrödinger equation is time derivative equal I second derivative of space plus potential.
Yes.
And if you remove potential, external potential, you have just time derivative equal I second spatial derivative.
Yes.
And wave function of this thing is extended, it's not localized, it's sinus.
Yes.
And I'm saying if you will add to this Schrödinger equation self-potential, which is cubic nonlinearity, this is known from literature like nonlinear Schrödinger equation, you will have self-localized solution of this nonlinear Schrödinger equation. So it is kind of description of free space particle, but it's localized, it's not sinus, it's not extended like Schrödinger equation without any potential. Yeah? No. Okay, after talk.
They'll beat you with the heavy something.
I don't know, are you challenging the description in quantum mechanics of a free particle?
Yes. So. Okay, so as I say, these are speculative comments. I do not insist that they are true. So I'm interested to study this topic. Task particle in quantum well. Are the wave function of Schrödinger equation stable or not? Can they be stabilized if unstable or not? How they are related to the wave function of nonlinear Schrödinger equation? Which I know at least one.
But are you asking mathematical questions or is there any physics in this?
Now I'm saying about mathematical equation, but I'm sure there should be some physics, which should be related. Okay, so I'm saying that some people, maybe not only quantum, will be killed by something. Okay, now I say about another analogy between nonlinear physics and physics of particles. In physics of particle, the particles with half spin or integer spin are possible. In our case, the vortices with odd or even topological charge are possible. Why there should be difference between odd or even topological charge? Because for odd charge, any section of vortex is asymmetric function. For even charge, any section is symmetric. And in my feeling of this problem, it should give very different properties of odd or even vortices. I do not insist that think about this as a joke. So the results were explained above.
Is there any works on differences in interaction of odd or even vortices?
I've seen some differences, some interaction, some works about interaction of vortices, but they were 3D structures which were moving in one to another. It was collision. There are works, but I'm not sure that it was studied. But maybe. This is broad field, and people study it. Probably should be.
Well, galaxy collisions are studied.
Sorry?
Galaxy collision are studied.
Okay. So I'm finishing almost.
Yeah.
I suppose that this talk will be 1 hour. Is it okay? 1 hour. Okay.
Finished and then
So next analogy is discrete spectrum of dissipative soliton, and it is analogy of discrete spectra in quantum mechanics. Next analogy, most of you probably know existence of breathing solitons, when solitons display complex behavior or oscillating. And there are recent work about observation of Zitternbewegung. This was published in Nature 2010 recently, and I found this analogy. I don't know how deep and how serious these analogies are, but I like them and I would like to investigate them. Okay, are there more analogies? Building phenomenological bridge looks interesting for me. Okay. So, true conclusions. Okay, there are some technical conclusions. It would be nice to study analytic solutions of Ginzburg-Landau equations. As I told, it could reveal scaling laws of some parameters in described above optical problem. Another thing, technical thing, which, but I found it trivial because step to the left, step to the right, and we lose analytical solutions. So it became all very complex, and I'm not interested to go in very, very, very complex things. Okay, delay effects could lead to interesting results, but to me it looks also trivial because what is possible? The only hope for Turing is possible, and only different M of spatial mode is possible. So logical charts of spatial mode. Okay, noise looks trivial. Because for me, read above. So some people will beat me. Why? Because if it's small, it should be just decaying for stable solutions, but still it can lead to different switchings. So more important things looks to me. So there are last two conclusions. First one is to systematize knowledges about topology, dimension, shape of vortices, how they are observed in different fields, and to build the tree of life, where I guess the second hyperbolic could be common ancestor. And the last point, which I already announced, is that for me it would be interesting to build the phenomenological bridge between nonlinear physics and quantum physics. I'm not expert in quantum physics, sorry. Then you can beat me. So I'm finished. Thank you, and there are some samples. If you are interested, you can have.
Thank you, Pavel. Well, it's been a really long talk, but a couple of questions. Maxi first.
Can we take a look at your last equation?
Yes.
Okay, as Pera was pointing out, the nonlinear term here, the real part of the nonlinear term does not give stability to the equation. So if this is a complex Ginzburg-Landau equation, you should go to the following fifth order term.
Could go. Should. You can go also adding linear coupling, and it helps. It stabilizes solution.
No, that's not stabilized non-linearly. So
Sorry?
non-linearly doesn't stabilize, so you need to include. I mean, the stability of the equation comes from the higher non-linear order, then has to be negative. So.
No. It's 1908 work of Rismalamed shows that adding this thing here stabilize second hyperbolic solution in Ginzburg-Landau equation coupled to linear.
G2 negative.
Oh, this I'm not sure. Coefficient can be different. But it's stable. We have stable
That's more likely with G2 negative positive and G0 greater.
G2 is here. Real part is negative here, right? So here is one linear term which is here. Here is another linear term which is here. So if you want real linear term, you should consider some combinations of G0, G2. Non-linear term is clear, only G2. So this equation, this system properly describes the optical problem which I explained above. Laser with frequency selective effect.
Emilio?
I have at least two comments and one question. First comment is that you say that there is an analogy between the spin one-half particles and the odd vortices. I don't think so. The spin of the vortices is always an integer. 0, 1, 2, 3. And there is you can have half integer charges with a complex vector. With a complex field. You need no. Okay. There are examples of fermion-like defects. If the field is not a complex field, but it is a director field. You have not a vector field, but a director or a vector without arrows. Then you can have spin one-half charge. But in optics, you don't have this. You have, for example, in liquid crystals, you can have this kind of thing.
Wait, in three-dimensional vortex, you have both direction of momentum, angular momentum, and quantization, which is 1, 2, 3. So only integer topological charge is possible.
In optics, only integer, but in particle physics, you have
Wait,
one-half.
associate 1/2 to 1, associate 1 to 2, associate 3/2 to 3.
I think you should probably continue that topic.
So this was a comment. Then one question. You have eliminated the equation for the material gain.
Material.
I mean, you have an equation for the carriers.
Yes.
Is this? I mean, then you have effectively what is called a class A laser. Is this describing an elixir?
Partially, of course, people will beat me, but yes. Yes, I mean, this describes the steady state solution. Stability of lasers can be influenced by carrier dynamics. So,
No, but
it can be more stable.
if you eliminate systematically this coupling to the carrier density, then the diffraction term is no longer like this. It gets a real part.
No, if you don't consider.
If you just
Substitution. You can
you just delete it, of course, it does nothing change in what you don't delete, but you eliminate it systematically,
So,
the diffraction is no longer fully imaginary.
if you have carrier diffusion,
no,
if you have no, without carrier diffusion, this is exact elimination of carrier dynamics, and it does not influence special effects. You don't have special effects in carrier equation.
we can talk on this later. And then my second comment was that you have explained about hydrodynamic vortices, and you say okay, the velocity should be zero in the middle because you have velocity. This argument is only valid if the velocity field is purely two-dimensional. In real tornadoes, you may have say a surrounding field, but inside you can have either a singularity, as you say, or either a vertical flux upwards or downwards. In real tornadoes, I think what happens is that the velocity field goes up.
I was based on two-dimensional considerations.
So this is only applies to two-dimensional situations such as the optical field, not
But
not a fluid field.
No, wait. But that means that probably you have projection of field on two-dimensional plane. That means
in a tornado, the velocity field is not horizontal. It has an important vertical component, especially
yes,
in the center.
but the components in projection of velocity onto a horizontal plane, to my opinion,
These components should be zero. That you are right.
But there is a velocity.
But the third one is not.
A tornado sucks everything in the middle and throws it away.
Maybe, yes.
Yeah, it does. Maybe there is some movie that you see a car that has been taken off.
Okay, thank you. Okay, I think, well, the very last, very short.
A little comment, I think it's interesting on the nonlinearity of the Schrödinger equation. There are some people interested because it may lead to the collapse of the wave function in the measurement process. So Weinberg made a very, very long paper trying to see whether nonlinearity were allowed by current experiments. I think the conclusion is that so we're very, very small.
So then it can be cancelled for last conclusion.
Maybe.
Okay, so thanks a lot. There is coffee outside, except for the people. Good. You are very, very